Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to invite Gaurav Chaurasia for a talk here. Gaurav is finishing his PhD under the supervision of George Rotakis at INRIA on area of image-based rendering. Gaurav.
Thanks a lot for the introduction and a very good afternoon to everybody. I will be talking about my work on image-based rendering. So let's start from the basics. The basic pipeline in all of graphics is to first do scene modeling. You create a model of the scene, then you would need to do some editing of the materials, the BRDFs, design the illumination of the scene, and that's when you get the final result. But all of these steps required the intervention of trained artists, depending upon how good an image you want to get. And that brings image-based rendering into the picture, because anybody can take images, and if we could render the scene just from images, that would be really cool. So the problem with image-based rendering is that you can create novel views from input images only if you reconstruct the whole scene exactly from your input images. That turns out to be a very hard problem, and there's active research in reconstructing the geometry, the materials, and the lightings of the scene. But we can only do approximate novel views. So the challenge in IBR, or image-based rendering, is basically how do we create an approximate novel view, and what is an approximate novel view? So I'll try to answer all of these questions in my thesis. My work is mostly focused on the first part, which is how to create approximate novel views. And I was lucky to be part of the projects in the team which were on perceptual analysis of image-based rendering. So let me start by explaining the problem statement in more detail. We are trying to do image-based rendering of urban scenarios. So we are looking at data sets, at images which have a lot of architecture, trees, cars, geometry. We're trying to use handheld images captured with handheld cameras only. We don't want to depend upon laser scans. If we had this data, it would be great, but we don't want to rely on dense data. We would like to do this in as few images as possible. The example you see here is an example of a dense capture, lots of images captured of the scene. We would like to do this in sparser and sparser captures, because that allows us to do very large-scale image-based renderings of really huge data sets. And lastly, we'll try to approach the problem of free viewpoint navigation. Most existing work approaches the problem of view interpolation, where you jump from one input view to the other input views. But doing free viewpoint navigation is a much harder problem, and we would like to start working in this direction. So brief overview of image-based rendering. It all started with light fields and image-based modeling way back in '96. There's been a lot of work, as I said, on view interpolation. This field has spawned a number of other applications, like upsampling of videos and camera stabilization. And as I said, all of my work is focused on IBR of urban scenes, and we have a lot of commercial products in this field already, and all of these products use a very basic form of image-based rendering, which you just have one plane, you jump from image 1 to image 2 and just do very basic blending. We try to approach this problem and try to do as well as possible. A standard approach is to reconstruct the geometry of the scene, and then any pixel in the target view can be recreated by back projecting onto the geometry and reprojecting into the input views. This gives us, and the earliest work was indeed based on this approach, and this actually works really well if your geometry is good. As it turns out, the geometry of urban scenes, and for that matter, any data set with enough complexity is not completely accurate. And that's why most of recent work has focused on alleviating the artifacts we get because of slightly inaccurate geometry. For example, in this work, optical flow is used to fix ghosting artifacts. One, you've reprojected your input images onto a proxy. If there is an alignment issue, optical flow can be used to align these images back, and this works very well as long as your alignment problem is off by a few pixels. More recently, this is the works which was partly done at MSR, ambient point clouds are used for unreconstructed areas of the image. The assumption is that the main object of interest is very well reconstructed, as you can see here, and the background and the sky can fade in and fade out. So we try to identify the problems in reconstruction in multi-view stereo. We know that these approaches can give you sparse and noisy data if you don't have enough texture in your input images, if the texture is too random or too stochastic, if the geometry is too complex, and all of these issues are aggravated if your input images are wide baseline, if the spacing between input images is a lot and the overlap is quite little. So from the point of view of IBR, this is an input image and a depth map which we got from existing multi-view stereo techniques. The problem really is that it can be quite dense in some regions. For example, the trees is almost not there, very few depth samples, and occlusion boundaries are simply not there in the depth maps. So with this, we now know that the geometry estimation does not give us dense data everywhere. And for such areas, we will try to use image-based approximation. We'll try to use image warping. And the two main issues are, of course, occlusion boundaries and depth samples, which we are missing. So why image warping? Image warping, because it has been shown to work well for a small number of points. If you have a few pixels which can be reprojected reliably into the novel view, you can warp your whole image with this in a least square sense. So all of this was inspired by the camera stabilization paper of Liu et al. And we improved that to use a shape preserving warp, as I'll explain afterwards. And it's a more intuitive way of controlling how the input image is converted to a novel view. You can use depth to do that, but the effect of depth is more indirect. You don't know you can understand the artifact that you will get because of noisy depth, but if you design your algorithm on the basis of image warps, this is a more intuitive way of controlling how the image will be reprojected into the target view. So I'll now go first over my first project more briefly. This project was at EGSR a couple of years back, and this really served as a proof of concept that image warping indeed is useful. So we start with a bunch of input images. We reconstruct the depth maps for each of the input images by using standard off-the-shelf multi-view stereo approaches, and we mark all the occlusion boundaries approximately and we ask the user to mark all the occlusion boundaries, and I'll explain why we do this afterwards. So with this data, we have depth samples, and I said we're going to use these depth samples as constraints for image warping. Each pixel shown here in gray can be reprojected into the target view, but all the white areas cannot be reprojected because they have no depth. At this moment, if you overlay a big warp mesh on top of this, a grid, and use each of the gray pixels to reproject the whole mesh, then you can probably handle the empty regions. And that's what the shape preserving warp is all about. So we have the reprojection constraint, which comes from depth samples. So we overlay a big sort of a quad mesh on top of the whole input image, a 2D mesh. Some pixels, as shown here, have depth. We can reproject these pixels into any target view, and we can warp the whole mesh along with it. To warp the mesh, we need to hold the whole mesh together by some kind of 2D constraint that we use as a shape preserving constraint, which enforces that each triangle of the warp mesh is only allowed to undergo a translation on the image plane, a rotation, or an isotropic scale. The end effect is that each triangle does not undergo arbitrary affine deformations, and that preserves the local shape of the warp mesh. But this, as you would notice, is a smooth image warp, and this will be a problem at occlusion boundaries because the background will move at a different speed compared to the foreground. And this indeed is a problem, as you can see in this not very well done illustration. If you have some points in the foreground in green, some on the background in red, and you move the novel camera in one direction, the points will try to fold over each other, which is the case of occlusion when the foreground occludes the background. And the same thing happens if you move the camera in the other direction. In this case, the warp mesh will stretch because the background will move in a different direction than the foreground. And this will lead to artifacts as shown here. This is an input image. Moving the camera in opposite directions will lead to these kind of ugly distortions. So to handle this, we embed a discontinuity in the warp mesh. This is done in the form of an elastic band. So as I said, we marked all the occlusion boundaries approximately by hand. So we have these very nice edges around each foreground object. We insert a narrow band of triangles around these around the foreground objects, and inside these triangles we do not apply the shape preserving constraint. This makes sure that this area is allowed to deform arbitrarily, but the rest of the mesh does have the shape preserving constraint, and that stays the way it should. The end effect is the part above this elastic band shown here does not affect the part below, and these two parts can move in opposite directions, or they can even fold over. And this constraint was the main contribution of the paper. This showed us that you can even use smooth image warps for doing a discontinuous sort of effect. At the same time, you have to maintain the shape of the foreground object. Imagine an object which has a right angle, there's a horizontal edge and a vertical edge, and you want to make sure that this right angle stays the same while you're warping your image to the normal view. To constrain that, we constrain the angle between any two neighboring edges of the foreground object. With these four constraints, we get the full image warp energy function, and we solve it in least square sense. And that the effect of all of this is the earlier distortions which you saw are now contained inside the elastic band which we marked earlier. So the red region shown here was in the beginning just 1 pixel wide, but warping the image to different places allows all the distortion to be absorbed inside that narrow band, and we know where the distortion is, so we can use other images to fill content into these areas. So now I'll go over the rendering pipeline. I hope you can see the input cameras. Okay, yes. So the input cameras are all shown in gray. The target view, for each target view, we pick a few input images, warp them, and blend them. I won't go into the details of blending. So here are some results. So on that side, you see results of earlier approaches. That's unstructured lumograph with the best quality model that we could obtain. And you would notice that we get ghosting artifacts there because the model was not perfect. And here, we don't have the same ghosting artifacts. The results aren't perfect, but we managed to improve significantly on occlusion boundaries. In this case, you will see the whole tree moves at least as one block, and it's not broken up completely. All the novel camera paths here are not quite view interpolation, but almost very close. They're not very free viewpoint yet. And the reason we could not do completely free viewpoint rendering was because we used a global image warp, and this led to distortions when you move too far in or too far out. So I'll show some comparisons of these distortions afterwards. The major limitations were, first, it was a global image warp and this led to distortions, which I'll explain later. And second was that we had to ask the user to mark all the edges manually, and this led to a problem. I'm sorry?
In addition to marking the edges manually, do you also have to somehow specify the Z order so that the tree moves in front of the building, or is that automatic?
No, that's automatic because you do have a reconstruction, so you can use that to infer the ordering of things. And as you can see, this would be a painful process. If you have to do the same thing for every single image of every single data set, makes this approach not very practical. And being a global image warp, it was real time, but the system was quite big. If you're trying to solve a warp mesh for the whole system, it became quite big, and more so because we had to embed these elastic bands. So it was a conformal de Delaunay triangulation, and that made it even harder. It had numerical issues and other problems, and lastly, as I said, we had distortions. So to address these issues, we did the paper which I'll present at SIGGRAPH in a few days. Mainly, the main targets were to do something completely automatic, not depend upon manual intervention, be real time, make it easy. So for this, we will again use 2D image-based approximations. To get occlusion boundaries, we've used image oversegmentation. So you divide the image into lots and lots of superpixels, and these superpixels they always capture all the occlusion boundaries. They have lots of other edges, but we can handle that because we're using a shape preserving warp. I'll explain that in a bit. To handle areas with no depth, we add some fake depth, some approximate depth in these empty areas. It's important to note that the depth we'll add is not photoconsistent. It's only useful for doing these approximate image warps. You cannot use this depth to help you in surface reconstruction. Third step is largely the same as image warp, but this time it will be a local warp applied on each superpixel individually, and this reduces the size of the warp and makes it much more easier to actually solve. It becomes much more lightweight. Last step is adaptive blending, where we'll try to alleviate artifacts which arise because of ghosting and popping. So the pre-process is largely the same. We again use multiview stereo to reconstruct a depth map for each input image. The second step has changed now. Instead of asking the user to mark the edges manually, we use image oversegmentation, and from this point onwards, the rest of the algorithm will operate on superpixels as the basic building block. So the next step is to add depth into empty regions. So here's a depth map and a superpixel segmentation. If you overlay these two things, I hope you can see it over there, that you have lots of areas which have lots of depth. That's all grand, that's all fine. But there are lots of superpixels which have no depth, which appear in white. And we cannot reproject them in any way in the novel view if we warp each superpixel individually. So to handle such cases, we can find depth from other superpixels which have the same visual content and are spatially close. So let's try to mark all of these problematic areas in green and look at any one of them, for example. So we have these two ideas to find approximate depth: spatial proximity and same visual content. First, let's try to find superpixels which have the same visual content, and these could be anywhere. And actually, if we rank superpixels by the order of similarity in visual content, we found that the rank 1, 2, 3, 4, 5 were always in sort of very different parts of the image. So you cannot completely rely on this. We had to incorporate spatial proximity. Problem with this is that if you put spatial proximity across the image plane and RGB difference into one weighted distance metric, you'll have to adjust the weights every time for each input image and for each data set. So to solve this, we use a superpixel graph. We have superpixels like this. We consider each superpixel as a node in the graph, and the edge between two superpixels is the distance between their histograms, their RGB histograms. And what this basically means is that an edge between two superpixels on the wall will be quite small because they have the same visual content, and two superpixels on the tree will also be low, but anything between the wall and the tree will be quite high. And histograms give you a nice way of evaluating this metric because the shapes and size of superpixels are quite arbitrary, but their content is supposed to be very homogeneous. So with this, you now have a graph for your whole image, and you're trying to find the best neighbor of the target superpixel shown in red over here, and you just want to refine, you just want to choose a few of these yellow guys you just want to find where to choose depth from. So let's zoom into this area and try to find any path from one of the red guys to one of the yellow guys. Path could be from anywhere in the image. And you can imagine the shortest path will be something that jumps over superpixels which always have the same visual content. So if you stayed within the tree always, that path cost will be small. If you ever jumped outside the tree, you'll immediately incur a big edge weight over there. So we retain this. So we rank all of these yellow guys by their shortest path cost, and we can find shortest path for all of these yellow guys, and we retain those which have the really smallest costs, and these have the same visual content because that's what we started with, and they are also close in the image. They are also more or less on the same scene object. Now it's important to understand that the reason we are choosing these three is not because they are close in Euclidean sense. They are close on this graph. This algorithm will converge to Euclidean sense if you had depth in neighboring superpixels. But if you did not, it could go and find depth from a relatively far off place without trying to find depth for the red guy from the wall, which is much closer actually. So at this point, we now have a superpixel where we wanted to add some depth. We found some candidates for it which have some depth samples, and we can interpolate these depth samples to add one pixel with depth into the target superpixel. So and we can, so I won't go into the details of this interpolation, and we can add a few depth samples. You could go on and add depth to every single pixel of the superpixel, but that's not required because we're about to use a shape preserving warp, and I'll explain why we need that. So we started with something like this with sparse depth, and we have added some of these samples artificially. Now we have something in every superpixel, and we're good to go to the next step, which is image warping. So now that you have depth samples in every superpixel, you could just triangulate these depth samples and reproject each of the vertices to get a target view. This will lead to problems because we added these approximate samples, and even if you look at the original samples, there can be a bit of noise, a bit of inaccuracies. So the effect of this tiny bit of noise can be seen on the balcony part, which was well reconstructed, but depth samples do carry a little bit of numerical errors. And in the top part, you'll see problems because we added approximate depth, same on the tree and on the bush. The result of our shape preserving warp is that it does not leave as many cracks, simply because we regularize the effect of depth samples. We're not, it's a least square smoothing. And as I said before, the shape preserving warp gives a straightforward intuitive way of controlling the effect of these depth samples. So let's jump into the warp itself. It's, yeah, as I said, these are the areas where we actually added depth samples in the previous step, and that's where you can see the best effect of the shape preserving warp. So the warp is exactly the same reprojection constraints, but within each superpixel, reprojected into the target view, and you can warp the superpixel like that. The shape preserving constraint is also the same. We try to make sure that each face of the warp mesh does not deform too much. And with this, we can now choose 4 input images to warp for each target view, which you can see on one side, and the final blended result on the other side. And let's now just take a brief look at the adaptive blending step. The basic weights for blending images for image-based rendering come from unstructured lumograph, a very old approach, but still holds good. These weights are based on orientations of cameras, choosing the closest cameras. The problem with these weights is that they blend too aggressively, and in such situations, you always get ghosting artifacts if you blend too much. And this is something that we found in another work, which I'll talk about in a little bit. So to handle this notion of adaptive blending, which means we want to blend only when absolutely necessary, we use this idea of superpixel neighborhood across images. So let's assume these 2 images, zoomed in area of 2 images, and 2 superpixels just marked artificially over there. These two superpixels will be considered neighbors if the depth samples of one reproject into the other. This means that there is some kind of correspondence between these 2 superpixels. They belong to the same part of the same scene object. If that is the case, it's probably okay to blend them. If at any pixel target view you're trying to blend 2 superpixels which are not neighbors and hence do not belong to the same region of the scene object, of the scene object, I beg your pardon, it's not a good idea to blend them because you will end up with ghosting artifacts. In such cases, we favor one candidate quite heavily. We increase its blending weight artificially, and that reduces the amount of ghosting quite a lot. And lastly, for any small cracks left, we just use basic hole filling to get the final result. Now I'll just show some free viewpoint results. In these cases, you can see that we're actually moving the novel camera shown in red quite far from the input images, and in this case actually really far from the input images. So this is taken from across the road, from in between on the sidewalk, and the images which are warped are shown in blue, and you can see that we do get parallax effects even though we move quite far from the input cameras, and that's the main goal of this project. We experimented with our approach on a number of input scenes. We can find more details in the videos and paper, and I would request you to do that. So we now compare two existing approaches. This is compared with floating textures, which used optical flow to alleviate ghosting artifacts. And you can see in this case, it was not designed for cases where the artifacts are really big. So it does not converge as well as it should have. And in this one, we compare with ambient point clouds, which uses this hazy point cloud for unreconstructed areas. Again, this was not designed for cases where your unreconstructed areas are actually on the main scene object, and then it looks like an artifact. And it's also important to note that ambient point clouds was a view interpolation only technique. It doesn't handle free view navigation. Lastly, we compared to our own approach, the one I explained before, and I said we get distortions when we move very far away from the input camera, as you can see in these cases. And it's also important to note that the new approach is completely automatic, where the old one required a lot of manual intervention, aside from being a bit slower and heavier for the machine. So the major limitation of our approach is that we do not handle sharp depth gradients within superpixels. We assume that each superpixel does not have a big depth gradient. If you're looking at any surface of the scene at a grazing angle, then any superpixels on that surface will have a sharp gradient. And if you try to warp this, it will warp more in one direction than the other direction, and the isotropic scale assumption of the shape preserving warp breaks down, and that's when we get artifacts. We would like to solve this issue by redesigning the shape preserving warp itself, and that's not completely inconceivable. So with this, I'm done with one section, which was the main work which was the main two projects of the PhD. I'll jump into two other projects where I was a co-author. So these were to understand perceptual issues in image-based rendering. The first paper was to understand the age-old question of blending versus popping. So you'll notice that in both of these papers, we used a very simple IBR scenario. We use simple scenes which have just a facade and a balcony in front. The proxy for the scene was just one big plane, as it is in applications like Street View. And lastly, the IBR approach used is probably the oldest one ever. Just apply texture map. And the reason we use these very simplified settings was to make sure that we have complete control on the studies. We have no other variables. Obviously, this has to be improved and generalized to arbitrary scenes, but we had to start somewhere. So in this paper, we'll try to understand this issue of blending versus popping. So that's basically what Street View does. You have panoramas at discrete places, and novel views are constructed by this sort of by choosing contributions from the two images. The scene geometry could be anything, but the proxy is always a flat plane. So in this study, we showed people image-based rendering results and a reference video along the same path, and they were asked to rate the level of artifacts in these videos. So for example, in this case, there's no blending. So you'll notice that the edge of the balcony really pops, and the popping is over a big distance because it's a sparse capture. There are few input images, so it jumps over larger distances. The second one, the popping is smaller but more frequent because you have more input images. Some other case in terms of blending, we again have a sparse capture where you can notice lots of hazy effects, especially on the banners over there, and lastly on this door. And part of the window, if you can see over there, has this big ghost, which is really in two very different places, simply because the sparse capture. And the dense capture would bring the ghosts really close and merge them, as you can see in this case. So we showed all of these one by one to the user along with the reference view, and asked them to rate all of this. And we got a strong guideline that people like seeing a sharp image which pops a little bit compared to a ghosted image which is just always has low frequency, which is missing high frequency details. For example, in this case, you notice it's using image 1, and then it pops to image 2 at some point. There you go, and then it uses image 2. People like this more than something like this, which is always a bit hazy. So you don't see the big artifact, the big jump, but it's always a little bit blurry. In the next experiment, we tried to understand what could be a compromise between blending and popping. So we use what is known as crossfade, where you use image 1 up to a certain point, then you fade between image 1 and image 2, then you use image 2. So this turns out to be a good compromise between, and the other cases, popping and blending are extreme forms of crossfade. A pop is crossfade of length 0, blend is crossfade of length complete path. So we again showed all of these with the reference views, and we got a strong guideline that crossfades for long durations are less acceptable than crossfades for shorter duration. Again, for the same reason that people like looking at a crisp image with a small sort of change and then again a crisp image. But this also shows that people are not good at noticing a perspective distortion. In this case, you can see it's distorting, it changes, and it's distorted again. But people don't seem to mind that, or they don't notice that. And that's the reason we did the next project, which was to understand this issue of perspective distortion. So now there's no blending, no popping, just a single input image with a single proxy, and we project this image onto the proxy, view it from different places, and we should see perspective distortions. This paper will be at SIGGRAPH this year, again in a few days. So for example, in this case, that does not look like a right angle. This is a single image mapped onto a flat plane, and the other one looks slightly more acceptable. So what's the limit? At what point can we say that the user will object to it? At what point the user will say, yeah, that does not look like a right angle? So the two experiments were to understand this idea of distortions. So we showed in experiment 1, we showed images, all these still images of facades with balconies, and we asked the user, what do you think that angle is? And the way they answered this was using a hinge device. It took us a long time to figure out how to ask this question, because if you put sliders, people will make mistakes all the time. So this turned out to be a nice way. People would see it and actually replicate the angle in front of them. So we recorded all of this data. In experiment 2, we asked people a very simple question. Does that look like a right angle to you? And people were asked to rate this from 1 to 5. And both of these experiments should give us data that matches. And that's exactly what we got. So I won't go into how we deal with this, all of this data. But the end result of all this was that we now have a model of predicting the level of distortions for any novel view position. For example, in this case, on the far right, you will see a top view of the scene with the capture camera and the proxy as used. The two dots over there are these two edges of the extrusion. And you will notice now that the user is trying to sketch, if it plays. Okay, so now the user is trying to sketch an IBR path over there, and red means bad distortions and blue means acceptable. So this, and we can decide the rating of this path using the data we already had. So this is among the first ways of predicting how bad the distortion will be without actually running the application itself. So I'll just let it go over again. So in the beginning you see it's quite bad, and then it gets acceptable. It's a very wiggly path, and then it gets to be okay. So what's the use of this? We can use this prior knowledge to restrict where does the user, to restrict the navigation zone of users. For example, in this case, we can only allow user to actually translate in acceptable. So you'll see like a blink effect where we actually stop the navigation at that point. We don't allow the user to go any farther. And we can do the same thing for turning. This allows the application to restrict navigation into acceptable zone. This is something that we do in games a lot. We restrict the movement of people within a fair zone. So the conclusions of all of this work is, first, we should focus on free viewpoint navigation. We have been doing view interpretation for a long time, and that's something we can handle quite well. Now it's about time that we jump to the next level. Second important idea that we want to push forward is we are trying to do image-based rendering, which is approximate by definition. So we can make approximations over reconstruction, over data we get from reconstruction, to do something more than that. Thirdly, because we are using some approximate data above depth, we should be using some form of regularization maybe in the form of image warps or something else, rather than just directly reprojecting all of this data into novel views. Lastly, IBR choices should be based on perceptual analysis and not what the first author thinks is good looking. So this work is actually being used in an immersive space with stereo in a European project. This is actually work in progress. We are porting everything to the cave. In the future, this will be the starting application used for a European project, which will work on using IBR for backdrops of games. So all of this code is already with the games company in Italy who are trying to work their way out of it. Open questions in image-based rendering. How do we use machine learning? How do we exploit all of this information we get from machine learning? There's a lot of work on semantic labeling of images, and we're simply ignoring all of this. Can we use this data to improve results? Secondly, they have all these nice ideas for image-based rendering, which have been around for quite a while. All the view interpolation work by Zitnik, the work on reflections last year, and our stuff where we focus on wide baseline stuff. Is there an approach which can bring all of these nice ideas together? I'm not talking about a switch case statement where you do this when in this case or do something else in some other case, but is there a nice way to combine the advantages of all of these approaches? Thirdly, IBR has been studied in so many different contexts. It's hard to compare one context to the other context. Light fields, for example, is one end where you have hundreds of images for one object, very structured capture. You can do amazing things with this. Street level IBR is 2 images for a whole building, and there's not much you can do with it. Is there a way to go smoothly from one end of the horizon to the other end? And how about artistic effects? We're trying to make things look good. We can use artistic effects to hide artifacts and give nicer immersive experiences, and some work is already there in the form of ambient point clouds, which use these nice artistic effects to haze out the whole background. And every time we write an image-based rendering paper, we always say it's real time, it's all very good. But the real question to ask is, does this actually work on a mobile device? If the answer is no, we have room for improving the efficiency of these approaches, make them very lightweight. That's the only place where this can be useful for. And lastly, we can use image-based rendering. If all of this works, we can then use it as a nice tool for virtual reality or for games where you have to make the backdrops in very quick time. After this, so all of this was stuff I've been doing. Right now I'm working on a project called Halide, which is a programming language which isolates scheduling from algorithm in image processing pipelines. So you can optimize both of these things in different ways. The code does not get entwined. You don't have to mix your algorithm into the for loops and vectorization code. So it's clean. It's supposed to make it's being designed to make life easier for people who write code. So this is in collaboration with the group at MIT. In terms of future research, I would like to exploit multi-view imagery in more detail. People do take lots and lots of pictures, but right now we're giving them tools to edit only one picture at a time, which means that if you edit only one picture, then you only want to keep one of them of all the pictures you took. At the same time, we are saying let's do image-based rendering, which is a nice innovative way of visualizing lots of pictures at the same time. So we have to give them tools to edit whole data sets at the same time, not just one photograph. And the edits we are talking about can be appearance manipulations. So these are some pictures I took, and if I want to change how the statue looks, I would like to do the edits in one image and get it propagated to all the other images automatically. This sounds a bit easy for static scenes, but once your scenes become more dynamic, if the scene geometry changes, if I have a friend in the picture and I want to change my edits on my friend, it becomes a harder problem. Interesting nonetheless. At the same time, we can try to change the scene itself. For example, this is where we emptied a metro station in Paris to take pictures in that station, and the problem was that they didn't like the advertisements. They wanted advertisements of 1950s. So how do we remove advertisements in one image and get that to propagate over all 50 images that we took over there? And this has to, respect all the parallax effects and everything. So that's a challenging problem. And what happens if I took very few pictures and I don't have enough data to propagate it from one to the other? Can I use pictures which other people took to do the same thing? That's the next level of all of this research. And finally, can we think of these very large photo collections as unstructured light fields? Light field is very structured capture, very small object, hundreds of images, and then you can do amazing things after capture. Can we develop similar functionality for these very large group of images? Can we think of them as unstructured light fields? Lastly, I would like to keep learning. I would like to explore machine learning and vision in more detail, work on image propagation and manipulation. This is something which I've been wanting to do in my PhD itself, but never had enough time to actually work on this properly. And I like being a part of groups which do lots of other things. A bit of work in systems and stereo is something which I would love to do. And my last project is sort of an example where I'm working with a compilers group to learn more and more things. With this, I would like to thank you all for your attention. I would be happy to answer any questions.
So all this right now running in real time?
Yes. I mean, this is completely real time. The pre-processing stages, of course, are like the whole reconstruction pipeline that is all offline. But the actual rendering runs at 50 frames per second without any problems, because the least square systems are now very small, easy to solve. We can use parallel cores to do all kinds of stuff. It's all real time. But as I said, the overhead is still there. You still have to store like 15 images to do rendering of a data set. So how do you optimize this? How do you optimize the amount of storage? How do you optimize the amount of memory stored on the GPUs and other things? That's where I mean by efficiency.
And another, you did nice work on an analysis of how far can I go and distort images when we have. Why not? Have you tried doing the opposite and trying to guide people when they capture the images where they should take?
Yes, this is actually something which we have thought about, but we never got very strong ideas. But this is actually a work so there's a paper by MIT where they're trying to capture a light field, and the system guides the person where to move the camera around, and that's very cool. But we would like to ideally you should be able to extend this to a multi-view environment where actually in this work we do get some guidelines of how many images to capture. It doesn't tell us where to capture, but it does tell, like if you see the heat map over there, if you have one image, that gives you this blue zone. If you have another image next to it, that will give you another blue zone. And then depending on how many images you want to use, you can make the whole thing completely blue if you use lots and lots of images. So that gives us a guideline on the number of images to use. This is assuming that you're doing a street capture where there's a car and there's not much you can do. You can't go forward or backward. But for handheld images, it would be good to explore this field.
I had another question. When you moved from using a single global warp for the entire thing to using local warps for each of the superpixels, doesn't that mean that the superpixels being warped independently can introduce lots of cracks?
Yes, it does, and that's exactly. You do get this. So we expected this problem to show up. Thankfully, so as a consequence of some accident and some design, this doesn't happen. First of all, because we're using a shape-preserving warp, the superpixels itself do not deform that badly. The way superpixel A deforms is quite similar to the way B deforms, and if they were neighboring in image at rest, they sort of maintain their shape in the next image. Same depth. Yes. But you get superpixels from other images which don't do this, which can be used to do some hole filling in the cracks left in between. That's exactly why you use multiple images to fill these small areas and give the parallax effect as you go along.
It's interesting that you don't notice a lot of either popping or ghosting in those cracks. I guess because of what you said, the warp is well behaved enough that
Right, it's consistent
neighboring
enough. It's consistent enough on neighboring views.
Superpixels have similar warps,
Yes.
which is what you'd expect if they have similar depths.
Yes, if your depth was accurate, then it'll always be really pristine. But that's what the warp is supposed to alleviate if you don't have exactly the same depth. And some of it comes from the blending heuristics, because in some cases, as I said, we do notice situations where you're not supposed to blend these two guys. So which one should you favor? And that's when we say, okay, choose the background. A parallax error in the background is less noticeable than a parallax error in the foreground. And that makes quite a lot of difference. It's a very simple idea, but it improves your experience by a fair margin.
Okay. Very nice
Thank you
work.
so much.
Okay.
Yeah, thanks.
Thank you very much.